So today we're taking a look at something called multiple alleles, which is actually super common, though in genetics, a lot of times we don't think about it. We should. So first of all, the term alleles. It's been a little while, but hey, what better time to review than right before the biology I learned. Alleles are the options that a gene can be. Drives me nuts when somebody says, I have the gene for blue eyes. No, you don't. We all have the gene for eye color. The allele is what options you can have. Blue eyes, brown eyes, green eyes. That's the allele, the option of the eye color gene. So you're getting your terminology wrong if you think that you have the blue eye gene. No, you do not. We all have the gene for eye color. What allele that you have, that's what gives you the actual color. So here's the thing, kind of like that example I just gave you. Think about how many different colors there are for eyes. There are more than 2 allelic forms. To a pretty large extent, Mendel got lucky. When Mendel worked with this stuff, there's just 2 options. But in real, well, I don't want to say real life, there are a lot of just 2 options, like what Mendel worked with. But a lot of times, it's not just green peas or yellow peas. In the example I just gave, eye color. It's not just brown eyes and blue eyes, there's also green eyes and black eyes and red eyes. There's a lot of different options for eye color. We're going to first take a look at all right, so rabbit fur color is one example of having a lot of allelic forms. Again, not just tall and short, not just purple flowers and white flowers, not just yellow peas and green peas. We have a lot of different options, multiple alleles. So rabbit fur color, hopefully you guys are ready to do a little bit of drawing today. Nothing too serious. I'm sure most of you guys are better artists than I am, and I can kind of manage to draw this. But if you're not great at it, it's okay. It works. And we're looking at rabbit fur color. So here's our little Peter Cottontail. That was not too bad. Probably the best one I draw all day. And one of the options is a full color. Ayla. which is a brown rabbit. I've got some colored pencils ready to go. If you guys have colored pencils, I'll give you a minute if you want to get them out. If you'd like to borrow some, I've got boxes of them back in the back there in the box. So feel free to go grab them if you like. Or if you don't want to add color, you're not hurting my feelings. All right, so our first phenotype is, again, what we call a full coat colored rabbit, which in this case is going to be a brown rabbit. And the allele for that is a capital C. As you guys can imagine, if it's a capital letter, it's dominant. So that full coat color is a dominant allele. What genotypes give us that brown phenotype, that full colored phenotype? Well, you can be homozygous, big C, big C. And then there's a lot of different heterozygous. When you have multiple alleles, it means you have a lot of different options. So you can be big C, little c, ch. Notice I underline my little c's. I like to do that for letters that look the same, big and little, like O, C, S. They look the same, big and little. The only difference is the size. I'm not such a great artist that I can draw, a huge difference between a big C and a little c. So I underline the lowercase letter. I think it helps. If you have a big C and a little c, h, you're going to have that dominant full color brown. And if you have that dominant C, little c, just like well, what that stands for, you'll have that dominant brown. So the last column here, if you can squeeze it in, the order of dominance. Well, as you can kind of tell, this one is dominant to everything. If you have that big C, it hints the big C. You have the big C, you're going to have that phenotype. This one is dominant to all others. Ready for our next drawing of a little rabbit? Yeah. A little bigger than the first guy, but pretty similar. So our second phenotype is chinchilla, which is a gray color of rabbit. All right, well, how do we get this chinchilla color? Little c, ch. Again, kind of like you guys remember we did the XY genetics, and we would attach a gene to the X, we'd link a gene to an X. Well, it's kind of the same thing here. We're saying, okay, it's recessive little c, it's why it's underlined. And then we've got that little ch to tell us that this is our chinchillin coat color. What are the options to have a chinchillin rabbit? Well, obviously, you'd be homozygous if all you have is chinchillin. And of course, you're going to be chinchillin. But there's also some heterozygous options. So you guys can kind of see CH, although it's recessive to the big C, it's still dominant to just plain H. We'll talk about that next. And it's dominant to just plain little c. So the order of dominance is that chinchillin coat color is dominant over what we call Himalayan. We'll talk about him next. And albino, we'll do him at the end. B. Thank you. Questions so far? Well, that's a big front foot. Yikes. Okay, next up, we have what we call the Himalayan type of rabbit. Himalayan around. And Himalayan rabbits are white with black trim. So he's got like black paws. Got a black nose and black ears. And voila, I've drawn Snoopy. The alleles for our Himalayan rabbit, little ch. You guys can imagine that little h there stands for the Himalayan. How do we get that? Well, Again, you can always be homozygous and get it. So you get two Himalayan, you're going to have a Himalayan rabbit. Or it is still dominant to just plain little c. Questions so far? We're doing all right still. So you're seeing how these all work together to create, again, multiple alleles, a lot of different options for rabbits. One last allele. And it's albino. As you might have guessed, albino is all white. No need for coloration on this one. His allele is just your plain old little tiny c. Which, as you might have guessed, is recessive to everything else. There's only one way you can get an albino rabbit. It must be homozygous recessive. It is recessive to everything else. All right, so there we see multiple alleles in action. A lot of different options. Now, you can only have two alleles. If you were a rabbit, you could only have two alleles. Yeah, one from your mom, one from your dad. And they can only have two alleles. They can only pass one on. All the rules still apply. It's just there's a lot of different alleles out there. Even though you only have two, doesn't mean someone else might have two completely different alleles. Same gene, different alleles. And that's the idea of multiple alleles. Questions? I got to turn the page, give you guys an example problem here. Anybody still writing? It's fine if you are. Absolutely fine if you are. Just let me know. Everybody's good? All right, so we'll perform a quick cross here. We've got a full-colored rabbit, but he's heterozygous with the Himalayan coat color. And we'll cross him with a chinchillan rabbit, who's heterozygous with the albino coat color. So as usual, we draw ourselves up a Punnett square. We put one parent on top, one parent on the side. It really doesn't matter which one goes where. One parent. There's the other parent. All right, now when you guys fill these types of Punnett squares out, you got to be careful. You got to slow down because you always want to list your genotypes in dominant order. So it's not always going to be the same. So for instance here, I'm going to start with the big C. That's dominant to everything else. So big C, little c, ch. But then when I come down, I'm going to list the little c, ch first because that one's dominant to Himalayan. Chinchillan is dominant to Himalayan. So even though he's listed second up here, I'm going to list him first down here because you always list your dominant allele first if you can help it. Do the same thing up here. Again, that big C is dominant to everything, so we're going to list him first. And then this time, even though C little h, even though that was listed second, I'm going to list it first now because it's dominant over a little c. So you got to slow down. You got to kind of think about what is your dominant, what is your recessive allele, and make sure you kind of list them out in proper order when you're working through these types. All right, now we need to analyze it, come up with our phenotype and genotype. Well, 50% are going to have the full coat color, but they're not the same genotype. So you need to kind of blast that out a little bit. 25% will be big C, little c, ch, and 25% will be big C, little c. So you see how they're going to have, these two will have the same phenotype, but they're not going to have the same genotype. So how to kind of differentiate them out. All right, we're also going to have 25% chinchillan. And this time we can just list the genotype because there's only going to be one of those. And we'll expect 25% Himalayan. Questions? Everybody see how that works, how to analyze them? Again, you got to kind of think about what is dominant to what. Kind of compare them, kind of list them out, kind of think it through. What's dominant to what? If you have two of these alleles, which one will come through? James. Questions? You guys are quiet today. Cool. All right, let's take a look at another example. Another very common example. You guys may have even heard of this one. Perhaps you know your own blood type. I hope you guys have heard of it because we actually did a lab on it first semester. Well, it was an E lab. Just, you know, you guys analyzed PowerPoint pictures if you remember properly. But still, we did talk about it. Now we get into the genetics of it. Why do we see the different blood types that we see? Excellent, excellent, excellent. Okay, well, blood. Your blood type, which is your phenotype. First possible blood type, type A. If you are type A, what does that mean? Well, it means you have A antigens on your body. So if you guys are on your blood cells, not on your body, on your blood cells. If you guys remember from first semester, antigens are proteins that exist on the surface of your cell, kind of make it recognizable. I'm drawing a triangle just as a specific shape. It doesn't necessarily mean antibodies are triangle. I'm just drawing it so you can see the specific shape. So your red blood cell would look like this, little triangles popping off of it. Those are the antigens, and that's how your body is able to identify it and say, hey, that's a friend. That's part of us. He's got the right antigens. Possible genotypes. All right. So again, we talked about all this first semester. Here's the new stuff. Genetically, how do you get to be type A blood? Well, as usual, you can be homozygous. I don't know why we always use I for blood types, what we do. I is always the letter for blood type. So if you're capital I, big A, you have A type blood. Or you could be capital I, big A, little I. Hey, that's a recessive little guy right there. No need for an underline on this one. I don't underline my eyes because they look different. Little I does not look the same as a big I. So I don't underline. All right, next up, we also have type B blood. I'm just going to draw a B antigen as a square. So if you're type B blood, it means you have the B type antigen, which again is just a little protein on the outer side of your blood cells. You guys remember this lab? First semester? Some shakes, some nods, some of you guys yes, some of you guys no. Well, good data review just before the bio ECA here. Well, how do you get to be B-type blood? Well, you can always be homozygous. Or heterozygous. Because B is dominant over little I. IB is dominant over little I. Anybody remember another type of blood? What's that? Don't say negative. We're not to negatives yet. We'll do O in a second. Good. O is definitely a good answer. A couple of you guys said O. What's the other one I'm looking for, though, right now? Excellent. Yep. There's also type AB blood. Oh, this is cool. This is cool. You have both the A and the B antigens if you're type AB blood. So your red blood cells have triangles and squares. Only one way genetically to have type AB blood. And that's to be heterozygous and have both the A allele and the B allele. Hey, what do we call this? What kind of inheritance is this? Learned about it last week. Two alleles, both are displayed. Excellent. Yep. Isn't this awesome? We've learned about multiple alleles and codominance. Both. Codominance, yeah. Codominance. A and B are codominant. They're both displayed. It's not a mixture. It's not like a house. It's not like half square, half triangle. That would be incomplete dominance. We have both of them displayed. Codominance. Excellent. All right, finally, you guys told me just a second ago, the other type, the fourth type of blood is type O, which can kind of stand for 0. Why 0? Because there are no antigens. You have a naked red blood cell. At least in terms of the A, B antigens. Only one possible genotype gets you type O, and that's little I, which, as you guys are probably figuring out now, I is little I, type OI, is recessive to either A or B. And A and B are codominant together. Okay, another cool example, multiple alleles and dominant recessive and codominance. So hang on, why did you say used to? Who was this someone? You'd have to find that story and let me read it. Because no, as far as I'm aware, O negative is still the universal donor. They can give to anyone because they don't have any markings on their blood cells. So no one else will recognize them as an invader. What's that? Mm-hmm. Yep, you basically have a naked blood cell, so no one else recognizes it. We're not going to get into it. You look back to first semester, but there's also antibodies, which again, we're not going to get into right now. But basically, you make the opposite antibody of your antigen. So someone with type A has B type antibodies. So they are looking for B type blood. If you give someone with type A blood, type B blood, they'd recognize it as an invader and then clump it together and potentially have a stroke or a heart attack or something terrible, and it wouldn't be good. A, B is terrible for everyone because A recognizes it, B recognizes it, and O recognizes it. People who are type O have all the antibodies and just no antigens. So AB can't give to anybody, and then type O can give to everyone. So they're known as the universal donor. No one's going to recognize a naked cell. No antibodies will find it. But I didn't hear that story that said that it's not any longer considered the universal donor. As far as I'm aware, it still is. But guess what? I'll be checking on the internet here as soon as class is over. See if I can't find that story. We'll get there in a minute. Promise. Questions on this page? Can I flip it? Do an example, blood type example with you guys. Yep. We'll get the positive, negative. I'm not there yet. You get there. I promise. I promise. It's on the positive, negative is on the docket today, and it's in your homework tonight. Wait a minute. Yeah. All right, so famous blood typing example. In the 1950s, a young woman sued film star director Charlie Chaplin for parental support of her illegitimate child. I'm sure I like that term. Charlie Chaplin's blood type was already on record as type AB. The mother of the child had type A and the son had type O blood. All right, well, there are two options for the mother, right? If she's type A, that means she might be IA, or type A little I. Charlie Chaplin, if he's type AB, there's only one option he can have. He can only be AB. That's the only way you can have AB type blood is to be IA, IB. So let's fill out the Punnett square. See what happens when these two people mix, make a baby. Well, over here we can have an A type child. All right, guaranteed to have an 50% A type child or 50% AB type child. But if mom is homozygous dominant, there is no way she could have an O type baby with Charlie Chaplin. It's not possible. How about with the little I, with the recessive I? Okay, well, again, we got a 50% chance of being type A, a 25% chance of being type AB, and a 25% chance of being type B. Huh. Guess what? It doesn't matter what the mom's genotype is. There is no way Charlie could have had an O type son. Not possible. Doesn't even matter if it's a son or daughter. He can't make an O type baby. It just can't happen. You're type AB. You can't pass on a recessive I allele. And there's no way you can have recessive eyes, two recessive eyes, if you don't get one from both your parents. How about that, huh? Questions? I wouldn't know why I'm in the 1950s. I'm not that old. I've read it, but I don't know if someone made it up or not. Yeah, so people here in class are asking if it's a true story. Um, despite my graying head of hair, I'm not that old. I don't know if it's a true story. I've read that it happened, but or she was wrong about who the father was, or she accused him of being the father when he wasn't. But yeah, he wasn't the father. Was not the father. Other questions? He could not have been the father. Okay, one last thing today. Yash has been asking about it. Ah, All right, so last little example, we've got the RH factor. You guys may have heard of positive and negative type blood. Well, that all has to do with the RH factor. Positive means you have it, yes, positive. Negative means you don't have it. Negative, nope. Much simpler than type A, B, and O. RH, positive, is just dominant to RH negative. So it's not multiple alleles. You either have it or you don't. There's no codominance. There's no incomplete dominance. It's just regular old dominant recessive. Plus positive is dominant to negative. I've still got plenty of room, but I'm going to turn the page just because I don't want to run out of room. If you have tons of room, go for it. There's no reason to turn the page. But I'm just going to because I want to get the question and the answer all on the same page. And I want to make sure I don't run out of room. So I'm going to turn the page. Everybody still writing? All right, last example today. All right, so work through this example. Call it a day. Take a deep breath. Woo. All right. A person with type AB blood who is heterozygous for the RH factor has children with someone with type O negative. What is the phenotype and genotype ratio expected for their children? All right. Well, once again, this is going to be one of those two trait crosses. Do you guys remember the big Punnett squares we have to do? You guys love them. Remember? If you don't remember, hey, what better day to review than today? So let's line up our cross first of all. So we have a type AB individual. So again, only one way to be type AB. And they're heterozygous for RH. So one big R, one little r. The other person is type O and negative. There's only one way to be type O, and there's only one way to be negative. You have to be heterozygous. So that's what these two individuals look like. So again, now we're looking at two different traits. So we need one of those big, gigantic, you love them Punnett squares. How do we know what goes down the side, what goes across the top? A lot of different ways you can do it. I like the FOIL method. Everybody's familiar with FOIL from algebra? So first, the I big A, big R, those are the first terms. So that's one possible outcome. FOIL, FO, the outside terms come next. So first, and little r. So I big A, little r, those are the outside terms right there on the outside. Little a. Codominant big A. Then we go to inside, FOIL, F-O-I, inside. That's I, B, R, big R. And finally, last, FOIL. Last would be I, big B, little r. All right, so there's one parent down the side. There's the genotype combinations they're going to make. Last parent or the second parent. Hey, this one's easy. There's actually not a whole lot of options here, right? If they're all homozygous recessive, even if we do it, all right, first, last, inside, last. Excuse me, first, outside, inside, last. Well, they're all little I, little r. That's always kind of nice. When they're all homozygous recessive, because it means we actually don't have to fill in 3/4 of our Punnett square, right? These are all going to be the exact same as this first one. We'll end up with the same ratios. So all we really have to fill in is just one column. Now, it doesn't always work out like that. It's a shortcut that you can take when you have 2 of the same, or 3 of the same, or 4 of the same, but it doesn't always work out like that. So watch it. Make sure if you're not going to do a big chunk of your Punnett square, make sure that they are the same. If you only have 2 the same, it still means you got to fill 2 out. So kind of watch out for that, but it's a nice little trick we can take. Keep your like terms together. So write your I's first, then your R's. Now we analyze it. What do we expect for the offspring, for the children? Well, 25% I big A little I, big R little r, and that would be A positive blood. 25% I big A little I, little r, and that would be A negative blood. 25% I big B little I, big R little r. This is going to give us B positive blood. And 25% IB little I, little r, which would be B negative blood. There we go. And again, had we filled out the whole rest of the Punnett square, we would have gotten the same results. I mean, 4 out of 16 is the same out of 1 out of 4. It still would have been 25%. So you're always welcome to fill out the whole thing, but if you ever notice you've got the same, you don't have to do duplicates. Save yourself a little time, a little handwriting. Don't have to do duplicates. Cool. Questions? Fun stuff, huh? People at home, fun day? Had a good fun day? Awesome feedback. You guys in here, you can't see them, but they're like hooting and hollering and clapping and stuff. They're all mute, so you can't hear them clapping, but they clapping. They enjoyed today. Just like the people here, they're going crazy now too. It's a fun day. Everybody enjoyed themselves a lot. Good. I enjoyed myself too. You guys were a